These days, we are tracking a cosmic visitor that has astronomers around the world recalculating, recalibrating, and frankly, racing against time to understand what is coming our way. The interstellar comet, designated 3I/Atlas, is now hurtling toward Earth at speeds that have exceeded initial predictions, and the mystery surrounding its trajectory is deepening with every passing day. This is not your typical comet making a gentle loop around our Sun. This is a rogue object from another star system entirely, and it is moving faster than anything humanity has ever built. We are talking about velocities up to 153,000 miles per hour, a speed so extreme that it crosses the distance from New York to Los Angeles in less than 2 minutes. And here is the crucial detail. Its behavior is not following the script. Outgassing from the comet's surface, triggered by solar heating, is causing unpredictable accelerations that are forcing scientists to adjust their models multiple times per week. The question hanging over every observatory right now is simple but unsettling. Where exactly will this thing go next? If you want to stay on top of this story as new data comes in, and trust me, it is coming in fast, make sure to subscribe and turn on notifications. This is the kind of breaking science that evolves by the hour, and you do not want to miss what happens next. Let's rewind for a moment and establish what we are dealing with. On July 1st, 2025, NASA's Atlas Survey telescope in Chile picked up a faint speck of light moving against the background stars. Within days, follow-up observations confirmed something extraordinary. This was not a local object. Its trajectory, its speed, its hyperbolic orbit all pointed to an origin far beyond our solar system. It was only the third confirmed interstellar object ever detected, following the infamous Oumuamua in 2017 and Comet Borisov in 2019. But unlike those two, which passed through relatively quietly, 3I/Atlas is putting on a show. It is active, volatile, and far more difficult to predict. The comet carries with it the chemical fingerprint of another star's planetary nursery, a frozen archive of materials that condensed in a solar system we may never identify. For scientists, this is a once-in-a-career opportunity to study the building blocks of worlds formed under completely different conditions than our own. But that opportunity comes with a challenge. How do you study something that refuses to sit still? To understand why this comet is so hard to pin down, we need to talk about non-gravitational forces. When a comet approaches the Sun, solar radiation heats its icy nucleus, causing volatile materials like water, carbon dioxide, and methane to sublimate directly from solid to gas. This outgassing creates the glowing coma and tail that make comets so visually striking, but it also acts like a series of tiny rocket thrusters firing in random directions. Each jet of gas pushes the nucleus slightly off its gravitational trajectory, and those tiny pushes add up over time. For a comet like 3I/Atlas, which reached its closest point to the Sun, what we call perihelion, on October 30th at a distance of about 130 million miles, the outgassing was intense. Solar heat at that range is powerful enough to vaporize surface ices at an astonishing rate, and the comet responded by brightening dramatically and forming a coma estimated to be tens of thousands of miles across. That is where the trouble started. Initial models, based on observations from when the comet was still far from the Sun and relatively inactive, assumed a fairly predictable path governed primarily by the sun's gravity. But once outgassing kicked in, those models began to fail. This contradicts what we previously thought about how quickly we could lock down an interstellar comet's trajectory. The more active it became, the more it deviated, and the harder it became to forecast its exact position weeks or months in advance. Let's look closer at the data, because this is where the story gets really fascinating. As of today, November 27, 2025, 3I/Atlas is approximately 300 million kilometers from Earth. That sounds like a comfortable cushion, and it is, but the distance is shrinking fast. We are talking about roughly 2 million kilometers per day. Now that rapid closure is not just because the comet is speeding toward us. Earth's own orbital motion is carrying us into its path, creating what astronomers call a geometric approach. Imagine two runners on a track converging toward the same point. Even if one is moving faster, the closing speed depends on both trajectories. Dr. Elena Rossi from the European Space Agency, who has been deeply involved in tracking this object, described it as two cars speeding toward each other on a highway. The combined velocity makes the rendezvous happen much faster than either object's individual motion would suggest. But here is where the numbers get tricky. At perihelion, when 3I/Atlas was at its closest to the Sun, its velocity peaked at around 246,000 kilometers per hour. That is roughly 68 kilometers per second, a speed that puts it in the upper tier of solar system velocities. As it slingshots away from the Sun and heads outbound, gravity is slowing it down, but it is still moving at a blistering 153,000 miles per hour relative to our frame of reference. The challenge is that outgassing introduces a variable acceleration that is extremely difficult to model without continuous observation. This is where missions like the European Space Agency's ExoMars Trace Gas Orbiter come into the picture. Between October 1st and 7th, while the orbiter was conducting its primary mission, studying the Martian atmosphere, it turned its instruments toward 3I/Atlas. The probe was positioned about 29 million kilometers from the comet, 10 times closer than any Earth-based telescope could manage at that time. This proximity allowed for what scientists call triangulation, a technique where observations from multiple vantage points, Earth and Mars in this case, are combined to dramatically improve positional accuracy. The data returned from ExoMars refined the comet's predicted position by a factor of 10. That is an enormous leap in precision. Before this observation, the uncertainty in the comet's position was measured in tens of thousands of kilometers. After triangulation, that uncertainty dropped to a few thousand. It sounds technical, but the implications are profound. It means we now know with much greater confidence that 3I/Atlas will make its closest approach to Earth on December 19th, passing no closer than 170 million miles, or about 270 million kilometers. For context, that is nearly twice the distance between Earth and the Sun. There is no danger of collision, no risk to satellites, no Hollywood-style catastrophe on the horizon. But the enhanced precision also revealed something unexpected. The comet's path is still shifting. So, what does this actually mean for our understanding of interstellar objects? Dr. Marco Micheli from NASA's Near-Earth Object Coordination Center put it bluntly in a recent briefing. No one expected this level of activity so soon. When 3I/Atlas was first discovered in July, it was still far from the Sun and relatively dormant. Early estimates suggested it would brighten modestly as it approached perihelion, but the actual outburst was more intense than models predicted. This is not entirely surprising because interstellar comets are shaped by conditions in their home star systems, which could be radically different from ours. The ice composition, the dust-to-ice ratio, the porosity of the nucleus, all of these factors influence how a comet responds to solar heating, and we have almost no baseline data for interstellar objects. We have observed exactly 3 of them, and each one has behaved differently. Oumuamua showed signs of non-gravitational acceleration, but no visible coma, leading to wild speculation about everything from outgassing of pure hydrogen to, less plausibly, alien technology. Comet Borisov, by contrast, looked and acted almost exactly like a solar system comet, complete with a predictable coma and tail. 3I/Atlas falls somewhere in between. It is active, it has a visible coma, but its outgassing is stronger and more erratic than Borisov's was at similar distances. This variability tells us that interstellar space is not a uniform environment. Comets from different star systems carry different chemical inventories, and those differences manifest in observable ways when they enter our Sun's domain. Now let's talk about something that has added another layer of intrigue to this whole affair. On November 15th, the Hubble Space Telescope captured a series of high-resolution images of 3I/Atlas as it moved outbound from perihelion. Embedded in the comet's tail, scientists identified what appear to be discrete fragments, possibly pieces of the nucleus that broke off during the intense heating near the Sun. Cometary fragmentation is not rare. We have seen it happen with solar system comets like Shoemaker-Levy 9, which famously broke apart and then collided with Jupiter in 1994, and more recently with comets like Atlas C/2019 Y4, which disintegrated entirely in 2020. But fragmentation introduces a new set of unknowns. If the nucleus of 3I/Atlas is shedding material, are those fragments large enough to alter the parent body's trajectory? Could they pose any independent risk, even a minuscule one, if they continue to break apart and spread out along the comet's orbit? The current consensus, based on the Hubble data, is that the fragments are relatively small, likely no more than a few dozen meters across, and they are following trajectories very similar to the main nucleus. But here is the thing. We do not have enough data yet to say that with absolute certainty. NASA is planning to release new high-resolution images later this week, and those could either put the fragmentation question to rest or open up entirely new avenues of investigation. Let me ask you something, and I genuinely want to hear your thoughts in the comments below. If you had the budget and the technology to send a probe to intercept 3I/Atlas right now, what would you prioritize studying? The chemical composition of its ice, the structure of its nucleus, the dynamics of its outgassing. This is not a hypothetical question. Space agencies around the world are already discussing rapid response missions for future interstellar objects, and the lessons we learn from 3I/Atlas could shape those plans. Drop your thoughts below, and if you are finding this deep dive valuable, consider liking the video. It really does help push science content higher in the algorithm, which means more people get to engage with stories like this. All right, let's keep going. One of the most striking aspects of this entire event is how much it has relied on international collaboration. The initial detection came from NASA's Atlas system in Chile, but within hours, telescopes in Europe, Asia, and Australia were trained on the object. The European Space Agency's ExoMars orbiter provided critical triangulation data. Hubble, operated jointly by NASA and ESA, delivered the fragmentation images. The European Space Agency's JUICE mission, currently en route to Jupiter, is also being tasked with making distant observations as 3I/Atlas crosses its field of view. This kind of coordinated effort is exactly what modern astronomy requires. No single telescope, no single space agency has a complete picture. Each observation adds a piece to the puzzle, and when you combine them, you start to see patterns that would be invisible from any one vantage point. But even with all of this firepower, there are gaps in our knowledge. We still do not know the exact composition of 3I/Atlas's nucleus. Spectroscopic observations have detected water vapor, carbon monoxide, and traces of organic molecules in the coma. But the relative abundances are still being debated. Different teams are reporting slightly different ratios, which could mean the comet is heterogeneous, with pockets of different ice compositions, or it could mean our instruments are operating at the edge of their sensitivity. We also do not know the nucleus' exact size with precision. Estimates range from about 1,400 feet to 3.5 miles across, a factor of more than 10. That uncertainty matters because the size directly influences how much outgassing can occur, which in turn affects the non-gravitational acceleration. Here is another wrinkle: rotation. Cometary nuclei are almost never perfectly spherical, and they almost always rotate. As the nucleus spins, different regions are exposed to sunlight at different times, creating a pulsing pattern of outgassing. If the rotation is fast, the outgassing jets can average out over time, producing a relatively smooth acceleration. But if the rotation is slow or chaotic, the jets can create jerky, unpredictable pushes that are extremely hard to model. We do not yet have a confirmed rotation period for 3I/Atlas. Some teams have claimed to detect periodic variations in brightness, which would suggest a rotation period somewhere between 12 and 24 hours. But others argue the data is too noisy to draw firm conclusions. This is the kind of detail that sounds academic until you realize it could be the difference between predicting the comet's position to within a few thousand kilometers versus a few tens of thousands of kilometers. And when you are trying to plan observations weeks or months in advance, that difference is the gap between success and failure. Let's zoom out for a moment and consider the broader implications of what we are witnessing. Interstellar objects are not supposed to be rare. Theoretical models suggest that trillions of them are wandering through the galaxy at any given time, ejected from their home star systems during the chaotic process of planet formation. Every time a giant planet migrates inward or a close stellar encounter destabilizes an outer disk, countless comets and asteroids are flung into interstellar space. The Milky Way should be teeming with these rogue wanderers, and yet until 2017 we had never conclusively detected one. Why? The answer is almost certainly observational bias. Interstellar objects move fast and spend very little time in the inner solar system where our telescopes are concentrated. They are also typically small and faint, making them easy to miss unless you are specifically looking for them. The advent of automated survey systems like ATLAS, Pan-STARRS, and soon the Vera Rubin Observatory has changed the game. These systems scan huge swaths of the sky every night, looking for anything that moves or changes. They are optimized to catch asteroids that might pose a threat to Earth. But as a bonus, they are also perfect for spotting interstellar interlopers. The discovery rate is already accelerating. We went from 0 confirmed interstellar objects in all of human history to 3 in just 8 years. At this rate, we could be detecting 1 or more per year within the next decade. But detecting them is only the first step. The real challenge is characterizing them. When an interstellar object zips through the inner solar system, we typically have only a few months, at best, to gather data before it fades from view and disappears forever. That was the case with Oumuamua, which was not discovered until it was already on its way out, giving scientists only a few weeks of viable observation time. Comet Borisov was luckier. It was discovered earlier in its approach, allowing for months of study. 3I/Atlas falls somewhere in between. Discovered in early July and reaching perihelion in late October, it gave astronomers a solid 4-month window to ramp up observations, and that window is still open. The comet will remain visible, albeit faint, until spring of 2026 before it exits the inner solar system for good. But even with that extended timeline, there is a sense of urgency. Every night of observation counts. Every spectrum, every image, every positional measurement adds to the data set that will ultimately be the only record we have of this object. Once it is gone, it is gone. It will not be back. So, what does this actually mean for the future of planetary defense and space science? One immediate takeaway is that our current methods for tracking near-Earth objects, while effective for local asteroids and comets, are stretched thin when it comes to interstellar visitors. The non-gravitational accelerations that plague objects like 3I/Atlas are difficult to model in real time, and they introduce a level of uncertainty that would be unacceptable if the object were on a collision course. Fortunately, 3I/Atlas is not, but the next interstellar object might have a different trajectory. What if, hypothetically, an interstellar comet were detected on a path that brought it uncomfortably close to Earth, close enough that even a small deviation from outgassing could shift it into a dangerous trajectory? Our current response time is measured in weeks to months. We would need to track it continuously, refine the orbit with every observation, and potentially make decisions about whether to attempt a deflection mission. That last point is purely speculative, because we have never attempted to deflect an interstellar object, and the challenges would be enormous. Interstellar objects are moving far faster than anything in a bound solar orbit, which means any deflection would require vastly more energy. But the conversation is already happening. Space agencies are wargaming these scenarios, not because they think a collision is imminent, but because the discovery rate is climbing and the window to prepare is narrowing. There is also a profound scientific motivation here. Interstellar comets are pristine samples from other star systems. They formed in protoplanetary disks around stars that may be hundreds of light years away, under conditions we can only infer from telescopic observations. By studying their composition, their structure, their behavior, we gain direct insight into the chemistry and physics of planet formation across the galaxy. Are other star systems making the same kinds of ice and rock that ours did? Or are there entirely different compositional families out there, reflecting different stellar environments, different abundances of heavy elements, different evolutionary histories? We cannot answer those questions with remote sensing alone. We need spectroscopy, we need imaging, and ideally, we need sample return. The idea of sending a mission to intercept an interstellar object and bring back material for laboratory analysis is no longer science fiction. It is engineering. The European Space Agency and NASA have both commissioned studies for rapid response missions that could be launched on short notice when a suitable target is identified. The technical challenges are immense. You need a spacecraft that can accelerate to interstellar intercept velocities, which likely means nuclear propulsion or some form of advanced ion drive. You need a trajectory that can catch up to the object before it leaves the inner solar system. And you need instruments that can operate autonomously, because the round-trip light time for communications could be prohibitive depending on the intercept location, but the payoff would be transformative. Now, let's circle back to the immediate situation with 3I/Atlas. For amateur astronomers and sky watchers, the comet is currently visible in the pre-dawn sky, emerging from behind the Sun as seen from Earth. If you have a small telescope, say 6 inches or larger, and you know where to look, you can actually see this thing with your own eyes. It appears as a faint, fuzzy patch, maybe magnitude 11 or 12, depending on its current activity level. It is not going to be a naked-eye spectacle like Hale-Bopp or Neowise, but the fact that it is visible at all is remarkable given its distance. By mid-December, as it makes its closest approach to Earth, it should brighten slightly, possibly reaching magnitude 10, which would make it an easier target for amateur equipment. Astronomy clubs and online communities are already organizing viewing campaigns, and some are even attempting to capture spectra using backyard setups. This is citizen science at its best, and the data being collected by amateurs is actually feeding into professional studies. If you are interested in getting involved, or if you are just curious about how to spot it, links and star charts are circulating on forums and in astronomy apps. It is a chance to witness a piece of another star system with your own eyes, and opportunities like that do not come along very often. But let's be honest about the lingering uncertainties, because there are plenty. We still do not have a perfect lock on the comet's trajectory past December. The current best estimate says it will pass at 170 million miles, and that is almost certainly correct to within a few million miles. But outgassing can still introduce surprises. What if the comet undergoes another outburst as it moves away from the Sun? Solar heating is decreasing now, so you would expect outgassing to taper off, but comets do not always follow expectations. Subsurface pockets of ice can be exposed by crumbling surface layers, triggering delayed outbursts weeks or even months after perihelion. We have seen this with solar system comets, and there is no reason to think interstellar comets are immune. If 3I/Atlas does have another outburst, it could shift the trajectory again, requiring yet another round of recalculations. And then there is the fragmentation question. If the nucleus continues to break apart, the mass distribution changes, which changes the way outgassing forces are applied. A smaller, lighter nucleus responds more strongly to the same outgassing jet, so fragmentation could, in theory, amplify the unpredictability. None of this suggests danger. Let me be very clear about that. The comet is not going to hit Earth. The odds of that are effectively zero. But it does mean that the story is not over. We are still in the data-gathering phase, still refining our models, still watching for the unexpected. Here is something I find deeply compelling about this entire event. It is a reminder that the universe is not static. We live in a dynamic cosmic environment where objects from other star systems can and do pass through our neighborhood. For most of human history, we had no idea this was happening. The sky seemed fixed, eternal, predictable. But now, with modern telescopes and automated surveys, we are seeing the true nature of our galactic surroundings. We are part of a vast, interconnected system where material is constantly being exchanged, not just between planets and their host stars, but between star systems themselves. Every interstellar object that passes through carries information about distant worlds we will likely never visit. They are messengers from across the galaxy, and learning to read those messages is one of the great scientific challenges of our time. So, where do we go from here? In the immediate term, the focus is on continued observation. NASA, ESA, and a host of other institutions are tracking 3I/Atlas daily, refining the orbit, monitoring for outbursts, and searching for additional fragments. Hubble is scheduled for more observation runs, and ground-based observatories are allocating time as the comet brightens slightly during its approach to Earth. Spectroscopic campaigns are ramping up, trying to nail down the exact composition of the coma and detect any unusual molecules that might hint at exotic ice chemistry. There is also talk of using radar, although the comet is probably too far and too faint for current radar systems to get a solid return. But if it brightens more than expected, radar could provide direct measurements of the nucleus size and rotation, which would be invaluable. Looking further ahead, the scientific community is already discussing what we have learned and how to apply it to future detections. The need for rapid response observing protocols is clear. The value of multi-wavelength, multi-instrument campaigns is clear, and the case for a dedicated interstellar object intercept mission has never been stronger. Let me leave you with this thought. We are living through the dawn of a new era in astronomy, one where the boundaries of our solar system are no longer the boundaries of what we can study. Interstellar objects like 3I/Atlas are opening a window into the broader galaxy, giving us direct access to materials and conditions that formed light years away. Every detection is a gift, a chance to expand our knowledge beyond the familiar confines of our cosmic backyard. But these opportunities are fleeting. These objects come and go on timescales of months, and if we do not seize the moment, the data is lost forever. That is why the work happening right now, the observations, the calculations, the collaborative campaigns, matter so much. It is not just about tracking a comet. It is about learning how to study the universe in real time, how to respond to the unexpected, how to extract maximum science from minimal time. And it is working. We know more about 3I/Atlas today than we knew about Oumuamua even after months of study, and that progress is accelerating. If you have made it this far, thank you for diving deep with me into this story. If you found this analysis useful, If it helped you understand what is really happening up there, do me a favor and hit that like button. It genuinely helps content like this reach more people, and in a media landscape dominated by headlines and sound bites, long-form science journalism needs all the support it can get. And if you have questions, theories, or just thoughts about what we have covered, drop them in the comments. I read them, other viewers read them, and some of the best conversations happen down there. Stay curious, stay skeptical, and keep looking up. NASA's new images are dropping this week, and I will be covering them as soon as they are released. Until then, this is the story of 3I/Atlas, an interstellar wanderer that is teaching us just how much we still have to learn.